Okay, please focus. In the last lecture, we studied multiple random variables or the joint distribution of several random variables. We took an example of, we also studied the way to store these distributions in multidimensional arrays, and I gave you a concept of what is a multidimensional array. Okay, that is basically, just to recap, you have numbers, a list of numbers, that's one-dimensional array. Now consider one-dimensional array as an element, one element. Okay, if you have those kind of elements, a lot of them, you store those elements in an array. That is two-dimensional array. Now consider a two-dimensional array as an element. And let's say you have a lot of two-dimensional arrays being elements. Now store them in an array. That's a three-dimensional array. Now think of this three-dimensional array just as an element. And let's say you have a lot of elements. Array of these elements is a 4D array and so on. Okay? So just to recap, you have, let's say, numbers 2, 3, 4, 9, let's say. These are elements. 2 is an element, 3 is an element, 4 is an element, 9 is an element. Array of these elements is one-dimensional array. Now consider this as a single element, another element like this. And maybe you have one more element or maybe several elements. Now, array of these elements, if you think this outer box as an array, then these are the elements inside the array. Yeah? Sorry? That's a two-dimensional array. Yeah. So this is array of arrays. And then if you have these kind of arrays, a lot of them. Let's say you have another 2D array, you have another 2D array, and you have a lot of them. Then this basically is a three-dimensional array. Okay? Make sense? And if you have a lot of 3D arrays, let's say you have another 3D array, just as the above one. This is not drawn properly, but think another 3D array, then another 3D array, then array of those 3D arrays is a 4D array. Then you have a lot of 4D arrays, array of those 4D arrays is a 5D array and so on. Clear? So, yes, question? Question? So last time I was telling you that how can we store a joint distribution if we have three random variables? Well, we saw if you have single random variable, this is just a one-dimensional array. I mean, these are different values. For example, the value of x is 2, value of x is 3, value of x is -1, value of x is 9, let's say. Then inside we can store the probabilities for different values, 0.1, 0.2, 0.4 and 0.3. That's a distribution for just x, let's say. Okay? That's a one-dimensional array. This distribution for this discrete random variable, what do we mean by discrete? I guess I have already told you that, but I tell you again, a discrete data set is basically a data set which is arrangeable, which is sortable. You can just arrange it and you can index first element, second element, third element, fourth element. If you can index the data, if you can arrange the data in indices, this is the first one, this is the second one, this is the third one. No matter the data values has points in them. For example, 3.5, 4.972, and 9 itself. This is a discrete set despite the fact that the values are floating point numbers. These are not the values, this is not the data type of the value. No. It is, can you arrange them to index them? So for example, if I have just these three, I can index, this is the first one, this is the second one, this is the third one. And even if I have infinitely many numbers, as long as I can index them, regardless of the data type of the object. The data type can be integer, the data type can be floating point numbers, the data type can be string, character, anything. Okay? If you can arrange them in an array, maybe an infinite array. If the data set is infinite, maybe an infinite array. As long as you can index them, the data set is called discrete. And if the data set is not indexable, no matter what you do, you cannot tell after this number will appear. There is no such ordering. You cannot come up with such an ordering. Then the data set is not discrete. For example, real numbers. If I give you real numbers and I ask you what is the next number than 2.1, you cannot tell me the next number. And you cannot come up with your own strategy of arranging these numbers so that you can index them. Okay? So that is not a discrete set. This is a so when your random variable take discrete values, I mean the total number of the set of the values a random variable takes, if that set is a discrete set, we call the random variable being discrete random variable. Okay? And the discrete random variable, the distribution for discrete random variable is also known as mass function. So you can call it probability distribution or you can call it probability mass function. So this is probability mass function or the distribution stored in just a single array. What if you have multiple random variables? Let's say x takes value 2, 3, minus 1 and 9, and let's say y takes value 0, 1 and 4. In that case, the probability distribution will be for every combination. For x is equal to 2 and y is equal to 0, what's the probability that x will take value 2 and y will take value 0? That's a number. What's the probability that x is 2 but y is 1? What's the probability that x is 2 and y is 4? In that case, a handy way of storing the distribution is a matrix or a two-dimensional array. In one side you have x values, in another side you have y values, and in each cell that the probability that x will take this value and y will take this value. Again, the whole matrix or the distribution must sum up to 1, just like earlier. So that's a 2D array. Yeah? Now think about 3 random variables, x, y, and z. There are so many different ways you can store this distribution, but one very handy way is a 3D array. So for example, this is x, this is y, and this is z. So think of a lot of matrices being concatenated together. Okay? So for example, let's say x is 1, 2, 3. These are 3 values. Y is minus 1, 5, 9, 6. And let's say z is 10, 20, and let's say 30. Okay? For x and y, you will be having a 3 by 4 matrix, depending upon whether you consider this x's as x or this as x. It may be 4 by 3 depending upon you take y here or x here. Okay? So if I take x here and y here, this becomes a 3 by 4 matrix. Yes? Now, this is the matrix for z is equal to 10. So, for example, x has total 3 values, x is equal to 1, x is equal to 2, and x is equal to 3. Then y is equal to minus 1, then y is equal to 5, then y is equal to 9, and then y is equal to 6. Okay, that's a matrix for z is equal to 10. So what's the probability, for example, that x is 1, y is 5, and z is 10? That is 1, 5, 10. This is the cell we are referring, whatever the number inside. Okay, now you will be having another matrix for z is equal to 20. That will be another 3 by 4 matrix. Okay, for z is equal to 30, you will be having another 3 by 4 matrix. You can stack them and make them look like this, or you can simply go with this case, that I have for z is equal to 10, I have a matrix, for z is equal to 20, I have a matrix, for z is equal to 30, I have a matrix. So what is the probability that x is equal to 1, y is equal to 5, and z is equal to 30, for example? So first of all, go and see z is equal to 30. This is the matrix. Z has done its job. Now go for x is equal to 1 and y is equal to 5 inside the cell. Okay? But remember, all these matrices, they must add up to 1. All the entries, they must add up to 1. Because it is a distribution. Make sense? So a handy way of saying is that this is x and y, and this is z. Z may have, for example, so z may have several different values. Okay? So that's a 3D array. If you have, for example, 4 random variables, x, y, z, and w, let's say, then you will be having these kind of structures as many as there are different values of w. So let's say w is equal to 1, this structure, yes, w is equal to 5, this structure, another structure just like the same. And maybe you have another value of w and so on. So get the idea of multidimensional arrays, and that's how the distribution of more than one random variables are saved. They are arrays in multidimensional. They are saved in multidimensional arrays. Make sense?
Yes.
Okay, great. Should I just give you a quick example in Python? So can you tell me the different values of x? How many different values of x are there? Your call. Just tell me how many different values x can take. 4. How many different values y can take? Okay, 8. How many different values z can take? 10. How many different values w can take? 2, 5. Oh, it's too much. Well, it can take these many, but just take a simpler example, 6. Okay. Now, this is not a valid probability distribution because the sum is not if you see the sum is not 1. Okay? Although the function I have used, it guarantees that every value is non-negative. No value is negative. It guarantees that. But it does not guarantee that the sum will be 1. Okay. It also guarantees that every value is between 0 and 1. The rand function guarantees that as well. But these are so many values, they are not adding up to 1. So to make this distribution valid, now you can see sum is 1. Okay? Sorry? I have just divided everything with by the total sum. Every entry is divided by the sum. So now if you add them together, you will get 1. Yes? So think for example you have 3 different values, 4, 9 and 7. And what you do is you calculate their sum. So their sum is 9 plus 7, 16, 20. The sum is 20 here. And if you divide every number by the sum, and now you add these numbers, you will get 1. Make sense? Now, assuming that x values, the values of x are 0, 1, 2, 3, the values of y are 0, 1, 2, 3, 4, 5, 7, the value of z are between 0 to 9, and the value of w are from 0 to 5. Now you can ask me the probability of this, comma, that, and you can x, y, z, w. Okay, what's the probability that x is equal to 2 and y is equal to 3 and z is equal to 1 and w is equal to 4? And that probability is not callable. So this is an array. I was using a function parenthesis, so that was my mistake. So this is the probability. Okay? Make sense? And you can store for 7 or 10 or whatever number of times. By the way, I have given you a programming assignment also, that you have to build a table, I guess, or for 3 variables or 2 variables. I do not remember whether I gave you. So it's 2 random variables. So I gave you an example to write a program for 2 random variables. Both will having total number of values being 5 and 5, and you have to find out a table in which x and y both they become independent. And I told you last time what do we mean by independence of random variables. If you have multiple random variables, for example x and y, and the probability of x is equal to, for example, 5 and y is equal to 7, if this is equal to probability, marginal probability of x is equal to 5 into marginal probability of y is equal to 7. Remember, we computed marginal probabilities from the joint, if you remember last time. So for example, what is the probability that x is equal to 5? Well, for x is equal to 5, just add all the values for y. That's a one complete row. That's a probability of x is equal to 5, and so on. If this is true, then we can think that x and y are independent. Here this comma is acting as and. Okay, just like in events, if probability of A is equal to probability of A intersection B is equal to probability of A into probability of B, then we say the events are independent. If the same is true for random variables, then we say the random variables are independent, but there is a catch in random variables. In random variables, we are not going to check just specific values. We need to verify that this formula is true for every possible value of y and for every possible value of x. Not just for x is equal to 5 and y is equal to 7, this formula should be true, or the left hand side should be equal to the right hand side, but for all other possibilities too. If that is the case, then we say the random variable x and the random variable y, they are independent. Make sense?
Yes.
Okay, great. So that was a very quick recap of what we have done so far, just to refresh everyone. Today we are going to talk about geometric random variable. Geometric random variable. Okay, the random variable is the following. I already have told you in the last lecture, I guess, Bernoulli random variable, which is just two values, x is equal to 1 and x is equal to 0. For x is equal to 1, we have some probability, let's say 0.7, which we call probability of success, and this we call probability of failure. Okay? It may be a coin toss. If the coin is not fair, then the probability of success is different than 0.5. If the coin is, if the coin is fair, then the probability of success is 0.5. Okay, but this is not just for coin. It is for every situation in which you have just two options, either this or that. In that case, you can model that using a Bernoulli random variable. So this is called probability of success. We can call it P, and this is probability of failure, 1 minus P. Okay, geometric random variable. Geometric random variable is the following. You repeat Bernoulli experiments. What is a Bernoulli experiment? You do the experiment, either you succeed or you fail. That's a Bernoulli experiment. For example, a coin toss. Okay? Can you tell me some other Bernoulli experiments? One is coin toss, either it's a heads or tails, just two possibilities. Dice is not a two-sided dice, which is a coin. Okay. Any other thing? Head tail? Yes, so tossing a coin. Anything else? Another experiment is, I don't know that experiment is random or not, you tell me. Here I'm going to tell you an experiment whose outcomes are just two, but it may not be random, or it may be random, you will discuss. The experiment is, you attempt a paper, okay, either you will score a grade A or you will not score a grade A. Yes? It's a Bernoulli experiment if the outcome is random. After attempting the paper and maybe knowing about the instructor, can you say for sure that I have scored my A or not? If no, then it's a random experiment. And this is Bernoulli experiment. Okay? Can you tell me another Bernoulli experiment? Repeat, please. So define the experiment. Experiment might be that given the target, let's say 300 something, or maybe whatever the target is, given the target, the team which is going to play the bat now, they will win or not. Okay? If they will win, x is equal to 1. If they lose, x is equal to 0. Okay? Now that's a Bernoulli experiment because it's completely random. We do not know. We cannot tell for sure x will be 1 or 0. But seeing the history, we can tell that the chances are this much that the team will win, otherwise the team will lose. So that's also a Bernoulli experiment. A third or fourth very brutal Bernoulli experiment is you just shot yourself and you will die or you will not die. Depends upon where you have shot, were you near the hospital at that particular time, so on. Get the idea? What is Bernoulli experiment? Now, I need your focus. Okay, so geometric experiment is the following. You keep on repeating Bernoulli experiments until you get a success. Whatever success you have defined and whatever the Bernoulli experiment is. You have a Bernoulli experiment, you do it. If you fail, you repeat it. If you fail, you repeat it. You keep on repeating until you get a success. And when you get a success, you count the total number of Bernoulli experiments you have done so far, and that number is the value of the random variable. Get the idea? For example, you keep on tossing a coin until you get the first head. The total number of tosses you have made until you get a success, the first success, that's the value of the random variable. Now it is possible that you toss and the first one becomes a head. In that case, the random variable x will take value 1. It is possible that you toss a coin, it goes on a tail, then you toss it again and it gets a head. In that case, the total number of Bernoulli experiments you have done are 2. Make sense? So the geometric random variable takes a value that is the count of Bernoulli random variables, Bernoulli experiments, till the first success. Okay? Now one thing that I want to differentiate here, when you do an experiment inside the experiment, for example, you are doing a Bernoulli experiment so many times and that whole thing becomes one geometric experiment. So when you are doing an experiment repeatedly inside an experiment, the inner experiment is sometimes called as trial. Rather than experiment, we call it trial. Let me write that out here. So rather than keep on saying, it is correct you say we are doing Bernoulli experiments, but statisticians, they normally say we are doing Bernoulli trials. Okay? So let's say the probability of success for the coin is 0.7. The probability of failure is 0.3. What's the probability? Now this y is a geometric random variable. What's the probability that y is equal to 1? What's the probability that you toss a coin and that's a head? Well, the probability that the coin succeeds, that is 0.7. Y is geometric. Okay? Now, what's the probability that y is equal to 2? That means you make 2 Bernoulli trials. The first one was failure, the second one was success. 0.5? How? No. Basically I'm asking this. Probability that y is equal to 1 is the same as probability that x1 is 0 and x2 is 1, where xi ith Bernoulli trial, the value of the ith Bernoulli trial. So probability that y is equal to 1 is basically the probability that x1, which is the random variable, is 0 and x2 is 1. x1 is Bernoulli random variable, x2 is also Bernoulli random variable. When I say xi, I'm saying ith Bernoulli trial, ith toss. Okay? So basically I'm asking what's the probability that x1 is 0 and x2 is 1. एक मिनट दीजिएगा. Now, ideally it should come from a joint distribution. So x1 is this, x2 is this, and we have this 0, 1, 0, 1. Whatever the probability that x1 is 0 and x2 is 0 here, x1 is 0, x2 is 1 here, here, and here. One of the boxes basically this is something we are interested in. But where this joint distribution will come from? Okay? Any idea? Okay. What if I tell you that the two random variables are independent? Let's say. Yes. क्यों? क्यों? ओ मुझे बताते तो सही यार. ये खत्म हो गया लेक्चर अब. पाँच मिनट आपने नारगली जाना है? चलें, we will resume from here on next time.